Start recording. So if I freaked you out a bit last lecture and you felt a bit overwhelmed, don't worry, you're not the only one, and that means that means I over-adjusted a bit. Previously, in the past couple semesters, I've had students get a false sense of security in the first 2 weeks and not be ready for loops come week 4 because they just would not be focusing their efforts. And so I do want you to practice. So I may have over-adjusted there. The homeworks haven't changed at all in terms of the amount of work you have to do. Still fairly light for the first few weeks. But we want to make sure that I personally like to expose you to a lot of things and then narrow in on the things you need. I mentioned a few things about binary, about binary operations that you don't need to know about, because that's kind of stuff that if you're in computer science and data science and IST, you'll take 1166, and that covers like binary arithmetic and that kind of stuff. Out of curiosity, how many people here are not CIS majors? Yeah, the vast majority of you. I know that. Most of you are not CS majors. It's good to point that out to the rest of the class. Most of you are not CS majors. The entire point of this class is to provide basically both a introduction to CS for students who are in the CS major but want to do it in Python. Introduction to provide a CS course for students who are non-majors. Provide an opportunity for non-majors who have no requirement, so your seniors, but who want to get some programming at the end, some people who are interested. So I try to cater to everybody with this class. So yes, it feels like a lot, but today hopefully you'll be able to see what we're focusing on. So today's lecture is going to be basically entirely focused on this short exercise. So if you go to if you open up Canvas, again, you can get to this in 2 ways. You open up Canvas, you hit modules, you hit module 2 overview. We scroll down. You hit Thursday will be a longer exercise over here. And that will bring you to input, compute, output. Otherwise, you can go to runestone.academy, like this. You can go to runestone.academy. You can log in. You can hit log in here. If you haven't created an account yet, do so. Remember, the course name is Spring 2024 Rosen. That's the course name. Hit the textbook and scroll all the way down to that appendix where it gives you the project list. And that will be how many handshakes, which brings us to input, compute, output. Skills required, statements and expressions, breaking down a goal. This will go over some. This one's a fairly valuable skill, especially if you're in one of the hard sciences, biology, chemistry, physics, as well as in the also the other hard sciences, psychology, sociology, just not recognized as hard sciences. The issue with psychology and sociology that doesn't get recognized by physicists a lot of the time is that with physics, you know a lot of the times what your known unknowns are. In psychology and sociology, you don't really know what those unknowns are a lot of the time, and that makes it actually really hard to study sometimes. So it's Anyway, so if you've taken a look at your homework for Lab 2, what you'll be doing on Friday and Monday, you'll be very excited to see this because you're like, oh, this is one of the things that we have to answer on Lab 2. That's like a free 25 points we're going to do in class. So, and if you haven't looked at that, when you look at part of Lab 2 and it looks familiar, reference this exercise we're doing in class. All right, so. And I'm just prattling on to make sure everybody's gotten the chance to log in over here. Okay, so input, compute, output. So here we're going to actually use Python as that calculator that I've been saying we're going to use Python as for a while. The idea here is that we want to it says that their goal here is to make and document is to help you understand about making and documenting simplifying assumptions and solving a problem by generalizing from a simpler version. The other thing that we're going to learn is, again, how to use this as a calculator, is something we can do. A lot of programs that we make early on follow this paradigm of input, compute, output. And in fact, a lot of our programs will do that. Just a lot of times our input statement is sometimes going to be implied. You'll find that we really kind of trail off around week 5 or 6 from using that input statement once we get into functions. The input function is really useful, but also it's slow because we have to basically enter in something every time. And a lot of times it's just quicker to have what we want to test in our code. But regardless, the idea here is that a lot of problems will just simply take an input from the user, throw it into the program to do some computations, do operations, throw it at equations, and then give us an answer. So this top one is an example of that problem, okay? Which is, first thing it does is that it's going to, the input states what the purpose of the program is. It says, enter a number of years and I'll tell you how many minutes it is. So for instance, I know it's tiny to see here, that message is right over here in this highlighted section. I type in 3, and it's going to tell me that 3 years is 1,576,800 minutes. Both seems like a lot and not very much, right? It's a lot of minutes, but also minutes are very small, right? So it can seem like, depending on your perspective, that's like a lot of time or like not a lot of time at all. Okay, so what does it do? Or how does it go about doing this? Let's zoom in a bit more. Years is equal to, so we create a variable called years, and we have the assignment statement. This says take what's on the right, store it on the left. Enter a number of years, and I'll tell you how many minutes that is. Okay, so so when I run it, that window popped up here, and it pops up in a window because I'm in a web browser. If you were doing it on idle, it would pop up in the console. It says, hey, I'll tell you how many minutes that is. I put in 3, and it stored the string 3 in years. When you ask for input, you're asking for text. So it stored text in there. It stored the string 3, right? It stored not the number 3, but like the 3 you might see if you were if you were reading a book. Not a 3 you would do a mathematical operation on. That's what the second line is. This int, open parentheses, years. Anytime you see like some word and then open parentheses, that's a function call. Input, and a lot of these are built, and the ones we're working with right now are built into Python. Input to get something from the user. Int takes something and turns it into an integer. It transforms it. If it can't transform it into an integer, like I put in enter a number of years and I'll tell you how many minutes that is, and I put in apple, you'll see that it gives me an error on line 2. And if you read the error, you actually get some information. They make more sense the more you learn. This one says it's value error. Invalid literal, so we know what invalid means. It's not good. Literal, so not a variable. For int, the function I wrote, with base 10 being, you may not be as familiar with I, so you instantly go, base 10, that the number system we're using. Apple on line 2. It's saying apple is not a base 10 number. It's a not a number, so I can't convert it. So program's going to stop. So if I put in 3, like the letter 3, it says, I can convert that to years. So what it does is that it takes the string 3, converts it to a number, and stores it in here. It converts it automatically like that. So from there, that gets our input done. The input is always ask the user for something, get some, change that input into whatever we need to use it with, typically a number, either an int or a float, and then store it. Here, just simply, you can think of this as that it updated and overwrote the value. Next is the compute. We need to transform from years to minutes. How do we go about doing that? Well, we have to make some, we either have to use an equation and or make some assumptions here. This program actually does both. So it said days is equal to years times 365. So first thing it said is like, if we want to transform years into minutes, then what we should do is that we don't want to go directly, because I don't know that information. I don't know the amount of effort it takes to go from a year to a minute. But I do roughly know how many days are in a year. And then if I know I know how many hours are in a day, and I know how many minutes there are in an hour, right? So we can convert from years to days, from days to hours, from hours to minutes. Make sense? So we can kind of just keep moving it down one at a time. So here, years times 365 is equal to the number of days in a year. And this is where I say it's an assumption, which we're going to come back to in a few weeks. This is incorrect. What is the right answer for the number of years? Sorry, for number of days in a year. 365.25? Yeah. Yeah, roughly about 365.25. It's roughly. You won't have to worry about this until you live to be until you live to the to see the year 2100. But the rules for leap years are a lot more complicated than you think they are. The year 2100 is not a leap year. You're like, it should be. It's divisible by 4, but that's not the rule. That's the old rule. It's the rule if years are exactly like this, years are more like this in a bit, you know, they're weird. But again, it's not really useful to have bits, you know. For the most part, this is roughly enough for the answer, 365. That's close enough. So we take the years, multiply by 365 to get the number of days. We don't divide because that would give us a smaller number, and we're going from a big unit that has a lot of things in it to a smaller unit. So it makes sense that since we're going from a big unit to a smaller unit, the amount we have would increase. Years to days. Okay, then we go from days to hours. We know that there are 24 hours in a day, so we take the number of days multiplied by 24. With me so far? Took the number of years we had, multiplied by 365, because that's how many days there are in a year. So that converted from years to days. Take the number of days, multiply by 24 to get the number of hours. Take the number of hours we have so far and multiply by 60. If we had 1 hour, we'd have 60 minutes. If we had 2 hours, we'd have 120. 3 would give us 180. Here we're ending up with a much bigger number because our hours was much bigger. And then we print it, and then we do this print statement, which we'll look at in just a second. 5 years would be 2,628,000 minutes. This print statement is pretty cool to look at. You've got print, and then open parentheses, and then rather than printing one thing, it has commas in between multiple things. You can print as many things as you want with print, and it will split it up automatically by spaces. It will automatically enter a space in between everything, which is why we have like an extra space here. So years is, so this is the variable years. So when it prints out this variable, it looks, okay, do we have this variable? Yes. We have this variable, so I won't cause an error. So what's the value inside of years? Oh, it's 5. So I'll print that out. And then I'll print out years is, and then I'll print out the value that's in the variable minutes, and then I'll print out the string minutes. Okay. So now, let's go ahead and try this out to go a bit. Now that you've seen this and I've explained this, let's go a bit of a step further. Okay? Let's go to seconds. How many seconds are there given a number of years, how many seconds are there in those years? So we want to modify this code to change that. Now, for some of you are like, okay, got it, let's go ahead. For a lot of you, you're like, I don't know how to get started on this. Well, we want to follow the same pattern when converting. We want to type in seconds over here equals, I'm going to leave to you. And then because our answer cares about seconds instead of minutes, instead of printing out the number of minutes, I'll print out seconds over here. So I'll print out whatever this variable is. Instead of saying minutes, I'm going to print out seconds over here to let people know that it's seconds. Make sense? So fill in the blank over here to figure out how many seconds are in that. And again, all we're doing is following the pattern we had. It'll take a few minutes to do that. For most of you, this shouldn't take too long, but for some of you, coding sometimes feels like defusing a bomb when you're, when you're first starting and you're like afraid to make any modifications. Remember, you can always rewind your code to the beginning in Runestone. So don't be afraid to take chances. he'll help me go over the second one. So let me get this printed out first. All right. So it looked like most of you got it fairly quickly. If you didn't, this is how we do it. Again, we're just extending the pattern here. We're going from hours times 60, store that into minutes. Then we need to convert the minutes into seconds. There's 60 seconds in minutes. So we multiply by that by 60 again. So we'll get this. So the number of seconds that will be in 5 years will be this multiplied by 60. So 5 years. And now that seems about right for the amount we had because we went from 2 million to 150 billion. So, sorry, 157 billion. So, let's see. Now, the other prompt is change the problem to go in the other direction. Given a number of seconds, how many years? All right. This is worth going into because now we're going to bring to bear one of the tools we had last time around. This one's a bit tricky. And for those of you who took a look at your homework, you recognize it. You might recognize that this part of this is useful because our homework says enter a number of seconds and give the number of hours. Or does it say give the number of hours, minutes, and seconds that is. So give me a number of seconds, convert that to hours, minutes, and seconds. So, but this is simply going to ask given a number of seconds, how many years is that? So how do we go about that? Well, first thing that I'm going to do is I'm going to just simply, I could erase all this code, sure. You could also comment it out like that. I'm going to just go ahead and start from a clean canvas. Okay, we want to go from, so we're going to reproduce this a bit. Seconds is going to be our input, like this. Input, the number of seconds, so I'm going to be lazy and just keep it very simple. Enter num seconds, gives back years. Okay, and then we can convert that into an integer again. And so now you're like, okay, so we're going from we went from small number to big number, that meant multiplying. Now we're going to go from big number to smaller number. We're converting and we're going in the other direction. We multiplied for one direction, that means we should probably divide for the other direction. Just kind of on the face of it, or you could just recognize that that is what you need to do mathematically. Either way that you come to that conclusion, it works. So we know the number of minutes is going to be equal to the number of seconds divided by 60. We're going to use divide here because we're just going to deal with whole numbers. Right? There's 60 seconds in a minute, so we'll divide by 60. So print. And here I'm going to skip down ahead and I'll end with a print statement so we can test what we're doing as we're doing it. Print seconds. And then comma, minutes. Always good to test your code as you're doing it. Never try to think, I've gone from having, so when I've been working like on a fresh assignment or a fresh project, I could count the number of times I've gone from having nothing to have a perfectly running program on one hand, without any errors, without any testing. It's happened to me like 3 times. Okay? In other words, it doesn't really happen. You got to test your code as you're doing it. So we print over here. I give it 1,000 seconds, and it's going to tell me 1,000 seconds is 16 minutes. Let's go ahead and do something we can do in our head. 600 seconds is going to be 10 minutes, right? 60 seconds multiplied by 10 gives us 600 minutes. It's good to check on things you know. All right. So now we can go to hours, right? So what's the next step to move to hours? Sorry? Minutes divided by 60. Yep. So we take the number of minutes. Sorry, we take the number of minutes, divide by 60 to get the number of hours. Hours is equal to minutes, divide by 60. And I'll update this to hours to print out hours instead. Save and run. 3,600 minutes gives us 1 hour, right? 60 minutes, 60 hours. Sorry, 60 minutes, each of which have 60 seconds. 60 times 60 is 3,600. That gives us 1 hour. So I put in 3,600. I knew I should get an hour back if it worked, and I did. So notice that basically, again, we are just going in the reverse of what we were doing. All right. So take a few minutes to finish that off for going from seconds all the way up to years. Now, why did he say this was tricky? Well, part 2 in itself isn't tricky because we're just going for years. But we'll take a look at part 3 very briefly, and then we're going to see the issue. Slashes because we only care about the whole numbers. Also, it's going to help us set up for the next part. Gotten to where they need to be. If you haven't, you're about to catch up. So, all right. Again, it's just the reverse of what we were doing earlier, which is we can compute the number of days from the number of hours by basically taking the number of hours and dividing by 20 and saying, okay, we have 24 hours in a day, so we'll take this number, divide by 24 to get the number of days, right? How many days are 48 hours? That's 2 days. You figure that out by taking 28 and dividing by 24. Sorry, 48 and dividing by 24. Similarly, we can go directly to years in the same way by saying years is equal to years is equal to days, divide by 365. I saw a couple students who went from days to weeks, weeks to years, perfectly fine. If you, it's one of those things where it really doesn't matter about how you convert it, because that's going to get you the same kind of idea. Now, the only thing, and then common error I saw is students would just not update this value on what's now line 7 in your print statement to be the variable that we wanted. They would have kept it at minutes or hours. Happens all the time. Or happens that we forget to print out the print statement and we're wondering why. Sorry, we happen to forget the print statement and we're wondering why isn't this printing out anything? So here I'm going to just simply say years. And I'm going to put in a rather big number because first off, if I put in like a number that's too small, like 10,000, it's going to divide by 60, then it's going to divide by 60, and eventually I'm going to have a number that's smaller. So like over here, I'm going to probably have a number smaller than 24. And then something that's smaller than 24, divide by 24, is going to give me 0, right? If I have a bigger number, divide, smaller. So sorry, if I have other way around. If I have a smaller number, divide, bigger number, it's going to be 0. Common question on the first exam is actually something along the lines of this, where we have our arithmetic operations, and you might see a question like this. This number, divide. And so what's the answer? 0, right? Small number, divide by big number, equals 0. Okay? So that is a very kind of easy way to just, if you see something, you don't need a calculator on the exam. If you see some horrendous math, it's fake math. So, it's trying to remind you of a lesson. So over here, we'll just simply run and we'll use we knew we needed 100. I'll do 100 million. So 100, 0, 0, 0, 0, 0, 0. And then I get 3 years, right? If I instead did single division here, we would get, 3 and however many left over. So 3.17 years. But there's a reason I kept it like this. And that's for the next part, which is applicable to what we need to do for your exam, for part 4 of homework 2, which is enhanced part 2, so you can print the number of years, months, days, and minutes. Now you might be thinking, oh, that's easy. Okay, so gonna go years, months, days, hours, minutes, and I'm going to put in 100 million. Sorry, 100, yep, 100 million. Was that 100 million? 1, 0, 0, 0, 0, 0, 0, 0, 0. Okay, plug it in and print. Very common mistake to make. And I make it all the time. Said, can't find the variable year, it's not defined. And it's exactly right. I wanted, my variable name is years, with an S, pluraled it, but I typed year, singular. Very common error. So, that was not an intentional error, by the way. I made that completely by accident. Okay, months. Oh, we don't have months. Some years, days, hours, minutes. Put in seconds. 1, 0, 0, 0. Okay. And we start getting things that don't make sense. So if this is years, 3 years, 1,157 days, 27,777 hours. This is just what happens if this is just the steps of our conversion. It's not telling us like those, and what it really wants us to know, what it really wants to tell is 3 years and however many days and however many hours and however many minutes. Like, if, for instance, if we were printing out the number of days and I put in 24 out, if I was putting in the number of, actually, let's go straight to the homework for a second, where it's asking you, given the number of hours, number of seconds, print out the hour, minutes, and seconds, that is. So if you put in 3,601, I'd want you to say that is 24 hours and 1 second. So how in the world would we do that? And the answer is modular arithmetic. Modular arithmetic. So here, we took the number of seconds, okay, and we divided by 60 to get minutes. That's going to leave some amount of seconds left over, right? Left over. A remainder, if you will. 60 seconds. So I had 100 million seconds. That's not evenly divisible by 60. So we're going to have some amount left over. I'm going to go at leftover seconds, we'll call it, is equal to seconds mod 60. And that will give me the leftover seconds. Instead of printing out the seconds, I'm going to print out leftover seconds. I'm just calling it leftover seconds just because colloquially. Now if I put in 100 million, I can get 40 seconds. 40 seconds was the number left over. That's the total number of seconds that we're not able to convert into minutes. I can then do the same for minutes. I could alternatively, instead of setting it out as a separate variable, I could do this. I could just do it right over here. I could have seconds. So we've already taken the amount that needed to convert from seconds to minutes, and I can do modular arithmetic. Remember, modular arithmetic is that thing where we get the remainder of an operation. Another way to think of it is it allows us to view, it takes the entire infinite number space, the entire space of integers from 0 to infinity and 0 to negative infinity, and instead compresses it into a small range that repeats on itself like a clock. So from 0 to 60 in this case. All the numbers from 0 up to, but not including 60. Once we hit 60, we wrap around. Just like with a 24-hour clock, how we have 24 hours. So with 24 hour, you have, 0, 1, you have midnight being 0 o'clock, 1 o'clock in the morning, 2 o'clock in the morning, 12 o'clock, 1300 o'clock in a 24-hour system. So we're ignoring AM, PM. We're just going straight into 1300. 1400, this class starts at 1400 in military time, right? It's a 24-hour clock. So and then when we get to 23:59, an hour before midnight, the next minute, that basically turns over back to and repeats back into 0 o'clock, right? That's a modular space. That's basically enforcing what this space we're working in is. So that's the kind of use that this has. So we can just simply say, okay, get the leftover number of the remaining number of minutes over here. We divide by 24 to get the hours. So, and we divide by 365 to get the days. And so now we know that 100 million seconds would be 100 million seconds is 3 years, 62 days, 9 hours, 46 minutes, and 40 seconds. Yes?
I don't get why you're doing the remainder part.
Why I'm doing the remainder part. Because at the end of the day, if I were to do, so let me go ahead and rewind for a second. We have all this, in 1 second, where is that? There it is. No, give me a second. Run. So we put in 100 million seconds, and we could say that's 3 years. But we know that 100 million seconds is probably a bit more than 3 years. It's not exactly 3 years. If we switch over to single division, which converts everything to floats, we get a more accurate but also not very useful answer. We get 3.17 years, which is both very useful, tells us that it's like, 2/10 of a year essentially, but also completely useless because how many days is 2/10 of a year, right? Because of the way our calendar system is set up, the way we count days and years is set up, this makes absolutely no sense. What in the world is 0.17? We don't know what that is. We don't know what that equivalent is to. So the task we just did, printing this out over here with the remainders, allows us to figure out and put this into a useful context. And yes, I realize I kind of went from the whole A and skipped all the way kind of to G when I did this. But let's go through it for a second. Let's go back over here where I was going with the leftover seconds. Okay? We want to, instead of printing out the number of years, we'll print out something a bit more useful. Years, comma, days, comma, hours. Normally I don't do this part in class, but I've decided, no, this should be done in class. So you can not struggle so much on the pain point that we have in our homework. Minutes. And then seconds. So I am just simply making that really long there, but hey, it's going to be worth it. And now if I put in however many, I'll get an answer. So let me put in a number over here. Say I put in 3,600 seconds. That should be the number of seconds in 1 day. And that should return that it is 1 day. Oh, sorry, 1 hour. 1 hour, not one. Should return that's 1 hour. And I get 1 hour and 60 minutes. Obviously, it's going to be 0 years and 0 days. So what we're doing is that in order to get the correct answer, we got to kind of count the amount of that's left over from our conversions. Okay? When we convert from minutes to seconds, okay, let's go ahead and say, let's go and work with units like over here. Let's just go with 65 seconds. 1 minute, 5 seconds. In order to get from 1 minute to 5 seconds, I needed to count the amount of seconds that were left over. Why did I need to do that? Well, because if I printed out the number of seconds there are, I would have just gotten 1 minute, 65 seconds, which doesn't really make any sense, right? 1 minute, 65 seconds. So I needed the amount left over, the amount that I couldn't convert into seconds. There's 65 seconds. How many of those seconds can't I convert into a minute? 5 of them. So modulo gives me the leftover. This gives me the quotient. This gives me the remainder. Okay. Now that we've got that, we are going to go ahead and now we're going to do that basically for all our units. Leftover seconds. We're going to go ahead and say for hours, hours is going to take the number of minutes we have and divide by 60 to get the number of hours. However, if we got more than 60 minutes, if we have like 62 minutes or something, that's going to mean that there's 2 minutes that don't get converted. So what we'll do is that we'll keep track of those minutes that don't get converted. Minutes is equal to leftover minutes. And then finally we do this, so over here, and again we'll test. Oh, cancel the test, because I need to switch this over to leftover minutes instead of printing out minutes. So we know that 3,600 seconds are in an hour. So let's go and add 2 minutes and 1 second. So 2 minutes is 1,200 seconds, so 3,600 plus 120 would be, 372, and then add 1 second to that. So this should give us 1 hour, 2 minutes, and 1 second, which is much more useful than just saying 1 hour. Yes?
If you put modulo straight into the other lines, like line 3 and line 5, would that be wrong?
Line 3, well, it wouldn't give you the quotient. And you'd be getting, and then you'd be taking the incorrect amount of forward to the other parts of the equation. So you typically do, when we do these modulo operations like this, we're typically moving pairwise. We're typically like doing, okay, here's the amount that I have and here's the remainder. One more on this, which is leftover hours is equal to hours mod 24. Okay, and so now, if I go ahead and plug in the actual answers that I want, let's see. Again, I would need to put in the, oh, no, I have 2 more to do. Leftover hours and leftover days. I don't have leftover days. We're here. And days mod 365. So here, when we figured out the number of minutes, we got the number of leftover seconds. Hours gave us the leftover minutes. Days gave us the leftover hours. Years gives us the leftover days. Okay. 3 years, 62 days, 9 hours, 46 minutes, and 40 seconds. Share code. It is 2:50. We're going to move on to make sure. I'm hitting share code. If you reload this page by hitting this button over here, or the equivalent on your web browser, you'll now have this in your timeline at the time that I shared it, which was about 2:50. So you just simply go to that timestamp and you'll be able to see the code. Yes?
What happens if you don't capitalize seconds, minutes, and the leftover lines?
Then if you don't, if you do this,
Yeah.
nothing as long as you're consistent. There's 2 ways, there's 2 schools of thought about how to write variables names that have multiple words in them. I come from Java, so I use what's called camel case. And the reason it's called camel case is that you write it like this. This is a variable name, and so you capitalize each new word. And it's called camel case because it has humps in the word. I know, it's a terrible name. Okay, programmers are terrible at naming things. It's just not what we're good at. The other way to do it is the C style way, which is what you'll see in your official Python documentation. This is a variable name with underscores between it. Use whatever one you like. I will use camel case by default because that's what I learned to do. And if you didn't capitalize it, doesn't matter so long as when you use it, you didn't capitalize it either, right? You just got to make sure it's that whatever you do, you follow through with it. Make sense?
Is there any
They'll prefer that if you should do what the already existing code base does. Honestly, it doesn't really matter so long as you're consistent within the function that you're working in. And we'll learn about, and basically, so long as you're working on the subproblem you're working on, as long as it's consistent in there, that's good. You don't want to have to remember, was it camel case or was it underscored, in other words. Just, in other words, in this class, do whatever you, once you choose one, don't switch to the other one in the same program. All right. So there used to be a series of interview questions at Google and Microsoft and other kind of questions, other kind of big companies that got a lot of flack because they seemed impossible to answer, because they are impossible to answer. Because the point of the question wasn't to get an answer, it was to see the problem-solving capabilities. Questions like this one: how many trees are in the state of Washington? Another similar question is, what is the amount of water that flows through the Mississippi River in a day? How heavy is the Empire State Building? These kind of questions aren't possible to answer. Not like off the top of your head. They seem like weird trivia questions. Which they are. But again, it's not about getting the answer. It's about the skill of coming up with an appropriate guesstimate. Okay? The ability to basically not be overwhelmed by a question that you can't answer and say, I'm going to make my assumptions. Here are my assumptions. Once I figure out whether we can go back and fix my assumptions later, but here's the assumptions right now, and I'm going to use those assumptions to generate an answer. Now, yes, doing assumptions like that can be dangerous. But as long as you know you're making assumptions, noting that you're making assumptions, and are willing to go back and fix your assumptions later, it's a good tool. Because the other option is staring at a giant question that you have no way of answering. Okay? A similar question by the Comic XKCD's, the webcomic XKCD's author, Randall Munroe, is estimating if all the digital data was stored on punch cards, how big would Google's data warehouse be? Punch cards, by the way, were the old way that computer programs were stored on paper. It's great that we don't have to do that anymore, because God's help you if you dropped your program when you were turning it in, because then all those pages would be out of order. Yeah, so Google happens to be very secretive about the amount of space it has, but they probably have more storage capacity than anybody other than Amazon, Facebook, or Microsoft. But Google is very big. And at least non-governmental. Only governments might have more. NSA might have more. National Security Agency. The NRO, another three-letter agency. CIA, you know about. NGIP, well, that doesn't link to that one. They've probably moved to a new server. NGA, National Geographical Intelligence Agency. U.S. satellite mapping for the military. And of course, the NRO, which was classified until the 90s. They have a pretty cool motto. They're the ones actually in charge of reconnaissance satellites. So, yeah, the U.S. has a lot of satellites, and satellites take a lot of data to have to store stuff. So what he does is that he figures out, instead of trying to figure out the punch cards and stuff and try to figure out that stuff, instead look at the amount of energy consumption they do. And they are happy to tell how much energy they consume in a year. So they're contracted to buy over 300 megawatts of power at 3 sites. So you can use that, figure out the number of watts a server takes up. 215 watts about is what was the ballpark estimate there. From there, figure out, okay, per server, how much can we store in a server? He figures out that's probably close to 10 exabytes, which is a heck of a lot. And then he just simply goes, okay, punch cards has 80 characters. a box holds 2,000 cards. So he figures that basically 15 exabytes of punch cards would be able to cover New England to about a depth of 4.5 kilometers. So in terms of the amount of data that would be needed. So again, it's an absurd amount of data that gets collected there. We also don't necessarily know where all of Google's data sites are necessarily. Although, again, the easiest way to find manned Google data centers versus like unmanned ones where they're just storing stuff is to ask taxi drivers and pizza delivery people, because they're going to be bringing it to people late at night. In fact, one of the memes online for people who are really into defense and intelligence stuff is you can tell whether stuff is going down in U.S. operations based off of the pizza delivery, busyness near the Pentagon. If pizza deliveries are happening to the Pentagon late at night, stuff is going down. So it's funny because it's true. So regardless, let's go back to our original question. How many trees are in the state of Washington? So those of us, I should say, who are from the U.S. and have lived on the East Coast our entire lives are probably very familiar with like kind of the urban jungle, the way we have things there, and we don't really appreciate how vastly empty the West is in the United States. There's huge swaths that are just simply preserved national park. It's kind of amazing. Washington has a lot of nature into it. In fact, let's go ahead and just pull it up over here. I'm going to open up a private window. So, maps.google.com. That way, not doxing myself. Okay. And let's just go to, let's just zoom out. So now everything just kind of becomes green here. But let's go ahead and scroll out to Washington. There's Washington. Beautiful Washington. Okay. Let's go ahead and there we go. Starting to respond. Let's go ahead at layers and switch to satellite view. That's going to be way more useful. Now let's get an outline by clicking on Washington. So there you go. So the right question is, how many trees are in this state? So let's make some assumptions. First off, about how much of this state would you say is forest? Based off of me clicking on it, how much of this state is forest? A lot? Sorry? About half. That's a good guess. About half. I like that one. It's nice and easy. Half. So I can say basically half of this is forest. We can also kind of assume that forest is going to be where most of the trees are, and that if it's not forest, there's going to be a comparably negligible amount of trees there, right? Certainly not going to be any trees in the water, not going to be any too much trees in the urban areas. You're going to get some smattering over here, but honestly, it will even out. Again, we're going for a guesstimate. So about half of this is forest. So if it has forest, it's got trees. Okay. So we figure out the number of square meters or acres in Washington. Okay. Divide that by 2. That's the amount of space that actually has trees that we can say is like tree dense. And then we got to ask ourselves, how many trees are in forest? What makes, what's the tree density there? How many trees per square meter, square mile, square kilometer, square acre or hectare, whatever kind of unit of measurement you need. That's something to look up, I would say, because you probably don't know that off the top of your head unless you're a forestry buff. So that should give you enough to go on to kind of start going with this. Okay, so go ahead and try cracking at this. Speak with the people next to you to help you on this one, by the way. Go ahead and collaborate. Try to kind of come up with a guess about how many trees there are based off of, okay, half of this is forest. How much forest, how much tree is in a forest, you know? Okay? This is one of those things that you're allowed to like talk about, but please talk with me. So what I would do is figure out how big is Washington, and then you say, okay, half of that is trees, half of that is forest. So divide the amount of space you have by 2. Then figure out, okay, given a forest, how many trees are there per unit? You know, whatever unit per desired unit, hectare, square kilometer, square meter, whatever you need. You can use, or you can get a unit for forest and convert it to whatever, or you can convert the number, trees per instance, you got trees per meter, convert that to square, not to mile. It's a conversion. see some kind of, okay, I know what to do, and some people that weren't necessarily clear about how to start. It's okay. It's a big question, and it's one of those things that's hard. So for the people who did get an answer, some answers over there. What was some answers I got? 3.4 billion. Okay, and then you got an answer all the way back there, I think you said. 4 billion? Yeah, 4 billion. Okay. Anybody get in the hundreds of millions? What about tens of billions? Because that's around the range. Yeah. 15 million? Probably a little small, a little on the smaller end there for that one. Because it's going to be, because what we're looking for, because it's most likely in the billions there. But how in the world do we get there, right? So first off, let's go ahead and figure out how big this place is. So when you looked up the Washington, what was the size of Washington we got?
66.5 thousand square miles.
6 to 6.5 thousand square miles. So 6,000 square miles, you say? Okay, 6,000 square miles. We'll keep. Sorry, is that what you said?
66.5.
66.5. 6,500 square miles. That sounds a bit more right. Let's see. Let's go ahead and check. Washington. Size. 71,000 square miles. 66.5, sure. Doesn't matter. Again, the numbers we use here don't really matter too much, so long as they're in the same order of magnitude. Size divided by 2 is equal to size. That's the amount of usable size I have, right? Or I should say that's the amount of forest I have. Forest is equal to size divided by 2. We decided that half of this is forest. So we can change whatever we have over here to be that. And then I'm going to steal what you said, at least in your equation. So we'll figure out how many trees is that total by taking the amount of forest we have and multiplying by, well, how many trees are... So what were some numbers that people got for trees in the forest? Yes? Yes? Yeah. You did in kilometers. So 100,000 per square kilometer. 100K per square km. Sure. What other units did we get? Yes? 150 per acre. That's the one I've seen a lot too. Okay?
I have 250 per square mile.
250 per square mile. So again, you can get different results based on what we do for this. So here, if we go by his numbers, 250 per square mile, since we use square mile, we can print trees, and we should probably be getting a fairly big number. Let's see, which he got as 8 million. Seems a bit small, though. So let's see, you said, what was your unit?
Acres.
Acres. So who has size of Washington in acres? Yes.
45,663,000.
45 million acres. And what was another one over there that I heard for acres? Anybody else have acres? 45 million acres. 45 million acres. And that gets us around 5.6 billion in the amount of trees. I probably just misheard what you were saying, which is why I didn't get the number with our first attempt. But the 5.6 billion acres, yeah, that's 5.6 billion trees. Yeah, and if you look that up, actually, you can't. This will be consistent. Number of trees in Washington State. You can see this is something that comes up around 5.5 billion. It says it's a lot of trees. Washington, the Forest Service says 9.4 billion trees. According to some, Cora says over 100 million. Certainly, a billion is more than 100 million. one of those. The urban forest of Washington has a estimated 2.5 billion trees. All right, but so again, this is sheer code. This is the kind of thing that it didn't take too much lines of code, but putting it in code allowed us to kind of write down our steps for it. We don't have too much time, but again, because of the way that the assignment is graded, I do want to do this last one, which is another one. How many handshakes for all the people in class? This is the last exercise, and when you're done with this, be sure to complete this questionnaire at the bottom. How many handshakes in the entire class? Okay, which is asking like if everybody were in here were to shake hands with each other. So this is obviously a question that was written pre-COVID. So if everybody in the class were to handshake with each other, how many would that be? And now when you get questions like this, the answer is to start small. So if there's one person in the class, we could either say that was 0 or 1. I'll put in a dash to leave it empty. If there's 2 people in class, there's only going to be 1 handshake occurring, right? But there's 3 people in class, you're going to have 3 handshakes. If it's Alice, Bob, and Carl, Alice needs to shake hands with Bob and Carl, and then Bob and Carl need to shake hands with each other. So 3 people, 3 handshakes. Seems about right. All right, if we add Dan into the mix, right, then that's going to be 3 more handshakes, right? Make sense? And if we add Earl into the mix, there were 4 people, A, B, C, D, Alice, Bob, Carl, and Dan. Add Earl into the mix for E. We're going to get, Earl now needs to shake hands with 4 people. So 5 people, that's going to give us 7 handshakes total, 4 more than we had previously. Let's see. Oh, sorry, 6 handshakes, no, 10 handshakes total. There we go. So if we now add in our 6th person, that 6th person needs to shake hands with 5 other people, bringing us to a grand total of 15. You may be able to see the pattern. Yes, no? So 7 people would give us, shakes hands with 6 people, so we add 6 to the amount we had before. The easy way to complete this table, by the way, is to take the number that's, so this part, the left side of the table is easy to complete. The right side, you just simply take what's above you and add what's to the top right. Sorry, to the top left. Now, the reason I like this question is because it actually deals with a particular number series that comes up a lot in computer science, which is the triangular number series, where namely 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, all the way up to some n value. Comes up a lot. When basically anytime they were trying to deal with all combinations in an intelligent manner. In other words, where A and B shaking hands is the same as B and A shaking hands. And in this case, it's a fairly straightforward thing to... So let's go ahead. The only thing that's going to maybe make it a bit weird is that we had this 1 as a starting point. But if we look up triangular, but I just told you it's triangular numbers. We look up triangular numbers, which is, by the way, what I'm going to be talking about tomorrow in 2168. Scary math. Who cares? It's just math, okay? It's got this series, like I was saying, just simply adding all the numbers 1, 2, 3, 4, 5, 6, 7 up to a point where you decide to stop. That's all that means. It actually turns out there's a formula for it. You take n, multiply it by n plus 1, and take half of that. And that gives you the formula. Now, does that work over here for us? So we experiment. Does that, in fact, work over here? It doesn't actually work over here. It gets close, though. So if I print out, so for instance, let's say that n is equal to, we've got 7, we're going to double check, we're just going to say, hey, 7 people. Okay. So n is equal to 7, print n times n plus 1. We're going to put that in parentheses because, again, the formula was n times n plus 1 in parentheses. And then we're going to do that in parentheses so we can divide by 2, just so we can make it that fraction. Parentheses are your friends. Don't rely on order of operations. It's going to get messy otherwise. So now if we save and run it, it should print out, well, it prints out 28, not 29. And the reason is because, of course, sorry, it prints out 28, not 21. The reason is because we have this weird one at the beginning, where it's like, what do we do with one person? But we notice that 28 is the next thing in the sequence. And if I plug in 6, that gives me the answer for 7. 5 gives me the answer for 6. 5 gives me the answer for 6. So instead, we can just do this. Subtract 1 from here. And then subtract 1 from that one, which is just effectively removing that plus 1 over there. And then that fixes our formula. So when we find a form, so the point of this is that sometimes you might be able to find a formula, and it doesn't quite fit, but it almost does. Maybe it's off by 1 or something. And there's 141 people in this class, let's assume. Hit run. That means that for everybody to shake hands with each other, they would need to, there would be a total of 9,870 handshakes, and hopefully a lot of washing of hands afterwards. Anyway, I just wanted to make sure that was done quickly. Sorry to speed through that because it is 3:20. I've shared this code with everybody. And again, please just fill this out. That is how you get your point, all the points for this exercise. I will see you on, today is Monday? Yeah, Tuesday. Forget what day it is sometimes. So, yeah, Tuesday. Okay, hit stop.